Hello, everyone. Welcome to the International Methods Colloquium. I am Justin Essery, an Associate Professor of Politics and International Affairs at Wake Forest University. The International Methods Colloquium is a periodic, online, interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by by Rice University and the National Science Foundation. This week's speakers are Patrick Wu of the University of Michigan and Jason Anastasopoulos of the University of Georgia. We are currently hosting a special series of presentations originally slated for the 2020 annual meeting of the Midwest Political Science Association that was canceled due to the outbreak of COVID-19. Each session will host two talks lasting 20 to 25 minutes each, followed by 10 to 20 minutes for Q&A. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And you can ask questions at any time during the talk, but all questions will be held until the end of the presentation. A link to each presenter's slideshow and paper, if available, will be present in the Zoom webinar chat window so that you may refer to it throughout the presentation. And I will post those links right after we get started. Our first presentation will be from Patrick Wu from the University of Michigan. He's presenting a talk entitled Joint Image Text Classification of Tweets Using BERT and CNN. This project is joint work with Walter Mebane, also of the University of Michigan. Patrick, welcome.
Thanks so much. So this is joint work with Walter, and the title of our project, Joint Image Text Classification of Tweets Using BERT and CNN. So oftentimes, we need to jointly consider text and images to make a classification. So this is an actual example from our data set. So it shows an image of a long line, and then the tweet says, early voting lines in Palm Beach County, Florida. And let's say that we were interested in making a classification about tweets that were observing long lines at polling stations. Just looking at the picture itself, we wouldn't necessarily be able to tell that this was a long line at a polling station. We see a lot of people waiting around. There is a sign that says early voting, but we don't know if that's an advertisement or indicating that it's a polling station of some kind. If we only looked at the tweet itself, the tweet says early voting lines in Palm Beach County, Florida, but nothing about the tweet indicates that this would be a long line. Only by jointly considering both the image and the text together would we see that this is a long line at a polling station. So most approaches have focused on what's called a late fusion approach. A late fusion approach just means that we generate a probability for the text, we then generate a probability for the image, and then we combine these probabilities together using some predefined policy or some learned policy in order to make a final prediction. And so this is an example of one of these late fusion approaches. But more recently, within the last year, there has been greater focus on what's called an early fusion approach, which means that we're going to feed in the text and the image together at the outset, directly into the model, and then generate a joint representation for the image and text. This joint representation for the image and text can then be used in some downstream classification task. And the reason why so much attention has been paid to the early fusion approach is because it has a lot of advantages over the late fusion approach, and it has taken advantage of this new architecture called the transformer. So I'll explain in a few minutes what transformers are, but they are a relatively new type of deep learning model that can handle both sequential and non-sequential data. And transformers have really brought the transfer learning paradigm that was first made popular in computer vision to natural language processing. They have also become the key component in most modern multimodal classifiers. And as you can see, a lot of work has been really put into developing these early fusion approaches. And it makes sense because it helps us solve a lot of the issues that come up with late fusion approaches. But as you can see, a lot of the recent work has really couched on the, has really depended on the transformer architecture and this architecture called BERT. So early fusion approaches have dominated late fusion approaches in terms of performance, but there are drawbacks, and I'll discuss a few of them here. So the most important drawback that I see is that early fusion approaches typically requires that all observations must have both the text and the image. But this is often not true for social media data, where some posts have text only, some posts have image only, and some have combinations of text and image. So you get all sorts of multimodality here. And early fusion approaches either require a large training set or require extensive pre-training on image text data. So this is another drawback of these approaches. And currently, early fusion approaches are pre-trained on datasets such as Google Conceptual Captions from Microsoft Cocoa, but these image text pairings don't usually reflect the type of image text relationships that we're actually interested in. And that's because when we look at the text and the image, the text often extends or modifies the meaning of an image, rather than simply providing a short description of what the image is. So the proposed architecture that I'm presenting today uses transfer learning techniques from both natural language processing and cross-validation, and computer vision. And I'm not expecting you to understand this diagram from the outset, but what you should notice here is that we use a pre-trained language model in the form of BERT, and we use a pre-trained image model as well, ResNet 152. And I'll sort of explain each step in a second. But first, we have to cover some technical bases of the model. So the first thing we need to talk about is self-attention, which is the building block of transformers. Self-attention is a sequence-to-sequence operation, which simply means that a sequence of vectors are inputted and the same number of vectors are outputted. So we can denote the inputted vectors as x1 to xn, and we can denote the outputted vectors as y1 to yn, all with dimension k. So all of the vectors here have the same dimensions. What we're going to do is we're going to calculate each of the yi's as a weighted average over all of the x's. Notice that the weight function is not, the weight is not actually a learned weight, but is from a predefined similarity function. So one of the simpler similarity functions would just be the dot product. That is taking the dot product between xi and xj. And the actual implementation of self-attention is slightly more complicated, but this really is just the general gist of what self-attention is. We're going to feed in a sequence of vectors x1 to xn. We're going to get in a sequence of vectors as output, y1 through yn, and they all have the same dimensions. So the transformer encoder block is what is built using the self-attention block. And as you can see, we have x1, x2, and x3 that are inputted vectors. It goes through the self-attention blocks that I just talked about. It then goes through a layer normalization. It then goes through a feed-forward network, another layer normalization, and then we get the outputted vectors. And notice again that the dimensions of the x vectors and the y vectors are exactly the same. So that means we can actually take the y vector and feed it into another transformer encoder block. So the logic of this, the reason why we call it a block is because we can stack many of these transformer encoders on top of each other. So bidirectional encoder representations from transformers uses this transformer encoder block. And to be precise, BERT is 12 transformer encoder blocks stacked on each other, and it takes as input word piece embeddings. BERT is pre-trained on 2 language tasks, the masked language model and next sentence prediction. In the masked language model, words are masked out, and BERT must predict what the masked out word is. And in next sentence prediction, pairs of sentences are inputted, and BERT must predict if the second sentence follows the first sentence or not. BERT is pre-trained on books corpus, which is 800 million words, and Wikipedia, which is 2,500 million words. Then the weights of BERT can be fine-tuned on downstream tasks, such as classification of text. And I'll talk about this a little bit more, what I mean by fine-tuning. Because really, transfer learning is what makes BERT so unique and is the reason why so much work has been put into this sort of new class of natural language processing models. So transfer learning is best known in computer vision. So I'm going to give an intuitive explanation of transfer learning using computer vision and images. So what researchers found is that in deep convolutional neural networks, these different layers were learning general features throughout the network, such as shapes, edges, and so on. So we can first train the deep convolutional neural network on a large data set, such as ImageNet, which has 14 million images and 1,000 classes. Then what we can do is remove the final classifier and then fine-tune or extract features from the deep convolutional neural network for our own classification problem. So these new classes in our own classification problem don't even need to come from the ImageNet data. The classification layer will learn the associations between the image features and the classes of interest. So a very popular example that came from a tutorial was that the tutorial shows that it was able to tell images of bees and ants apart almost perfectly using only 120 images of bees and ants. And how they did this was that they used a classifier that was pre-trained on ImageNet. So even though bees and ants were not originally categories within the ImageNet dataset, what they did was they removed the classifier from the ImageNet classifier, appended their own classifier for bees and ants, and then they extracted features using the convolutional neural network and then classified based on those features into the categories of interest. So this really shows one of the advantages of transfer learning, which is that you don't need a lot of data in order to use really deep and modern neural networks. So BERT is based on this transfer learning paradigm as well. What we're going to do is we're going to first obtain BERT embeddings, also called BERT features, that are of dimension t by 768, where t is the length of the sentence. Then what we're going to do is average the BERT embeddings to get what is called a BERT document vector, and this is of size 768. And then we're going to use a fully connected layer to make a classification of that document, if our task here is to make some kind of classification. So unlike transfer learning in images, BERT is rarely used as a feature extractor. So that means you always have to fine-tune on the downstream task, which means that what you need to do is remove the classifiers that was used in the pre-training tasks for BERT, attach your own classifier on top, and then update and train BERT's weight to your own task for a few iterations. But the idea here is that because BERT's weight are already pre-trained on Wikipedia and the books corpus, it should perform better than if you were just using a transformer from scratch on your own text. So the proposed model uses 3 elements: the text, keywords that describe the image, and image features. And here I'm going to talk specifically about the bottom part here, the image keywords, and what I mean by that. So keywords that describe the contents of the image give deeper contextualization to the image. What I mean by this is we can automatically generate keywords for the image by using something like a ImageNet classifier, something like ResNet 152, and use the top classes that predict what is in the image. What we'll do then is feed the text and the keywords together into BERT. In order to separate the keywords from the text of the observation, we can denote the text as segment 0 and the keywords as segment 1. And so to operationalize this idea, we can use segment embeddings, which are learned embeddings that are added to the initial inputs to BERT in order to distinguish tokens from segment 0 and segment 1. The idea here is that because BERT is pre-trained on Wikipedia, including keywords derived from the image can give deeper context. So for example, if the image classifier identifies a Q, and we were to feed that word into BERT, Q into BERT, then BERT associates the image with the concept of weighting, even if the text of the tweet does not explicitly mention weighting. So after we obtain the BERT embeddings of the text and the image keywords, we can then linearly modulate each embedding based on the image features. And at this part, I'm talking about the top side of the proposed model. So what we're going to do is we're going to apply feature-wise linear modulation to the BERT features. What we do first is we use a pre-trained image model like ResNet 152 to obtain image features. We'll then use an affine transformation over the image features to learn parameters gamma and beta, which are called film parameters. And again, film stands for feature-wise linear modulation. So these are the parameters that the affine transformation is going to learn. We'll then apply the film parameters to the ICE sentences J's burst embeddings, denote this as Fij, as follows. What we'll do first is scale the BERT embedding for token J by gamma, and then we're going to shift it by beta. So this is why this is called feature-wise linear modulation, because we're applying a linear transformation on a feature-wise basis. So in effect, what we're going to do is we're going to upweight or downweight the embeddings based on the image features. So this is how the classifier is learning image and text features together. In order to apply the film parameters, we have to use a slightly modified version of the transformer encoder block. And here, this is really similar to the transformer encoder block I had shown a few slides ago, except that after the last layer normalization, we're going to have a film layer. And in this film layer, we're going to apply the parameters gamma and beta on a feature-wise basis. Then there's going to be a residual connection, another layer normalization, and then we'll obtain the modified BERT embeddings. So these film transformer blocks are the film blocks that were in the architecture diagram. So the diagram I had just shown you, this would be the film block 1, film block 2, all the way up to film block n. So the film transformer blocks would also be stacked on each other. So we can apply this feature-wise linear modulation multiple times. So a question arises, why not just concatenate the image features and the outputted BERT features, which seems like a really natural thing to do? So the key advantage of using film instead of concatenation is that it does not require every observation to have an image. What we can do is we can zero out the film parameters for observations that do not have an image associated with the text using indicator functions, which will effectively zero out the embeddings of the text without images entirely. This is why the residual connection that comes after the film layer is so important, because the residual connection after the film layer restores the embeddings. So what we're going to get is only the embeddings that have an image will be modified through this process. Using film parameters also allows us to control the flow of gradients using the indicator functions. So that means that only observations that have images will update the film parameters. And this is a key advantage of this method over other multimodal classifiers. Because in other multimodal classifiers, oftentimes the proposed way of getting around observations that don't have images is to simply randomly initialize the image. So the neural network is just learning from noise. But here we can make sure that the film parameters only get updated on observations that have an image. So for our application, we're going to look at tweets about election incidents during the 2016 US general election. So these are tweets that reported some kind of election incident during the 2016 general election. Tweets were first classified as either a report or not. Then for tweets that were classified as reporting an election incident, the paper included a deeper breakdown about what type of incident it was. These categories were then further broken down into adjectives. Also, it's important to note that tweets could belong to more than one type of incident. And for a full set of definitions, you can consult the original paper, which I've also linked in the slide. The paper uses an ensemble classifier for the multi-label problem, but it doesn't use any information from images that users might have included. And there are only about 4,000 tweets that have hand-labeled categories and adjectives. So this is a pretty small data set, relatively speaking, which is why transfer learning is so important here. And this is the results of the binarized classifier performance. That just means that even though this was a multi-label problem, I binarized each of the categories and the adjectives and then applied the classifier in a binary fashion. So to read this table, the bolded lines are the categories and the A, B, and C underneath the categories are the adjectives to describe that. So the election incidents were classified first into the category. For those categories, they were then broken down into adjectives. And so we can see that the image and text BERT outperforms both the ensemble classifier and the text-only BERT on a lot of the categories and adjectives. And in blue are the categories that, or the adjectives or categories that the image and text BERT performed exceptionally well on, even compared to the text-only BERT. So for the adjectives no crowd or no line, the image and text BERT performed much better than the text-only BERT or the ensemble classifier. I also forgot to mention that these are F1 scores on the positive class. So these are what the metrics are showing. The reason why we went with the F1 score is because the data set is not balanced. So something like accuracy wouldn't be very helpful for us. This is why we went with something like the F1 score. So we can also see that both the text BERT and image and text BERT performed exceptionally better than the ensemble classifier for this adjective. To see more results, these are the final two categories. And again, we can see that especially for 5A, not able to register, and 5C, able to register, the image and text BERT perform much better than even the text BERT, text-only BERT, or the ensemble classifier. But that's all I have for you guys today. Thank you so much for your time, and look forward to your questions.
All right. Thank you, Patrick, for that presentation. Our second presentation will be from Jason Anastasopoulos, presenting a talk entitled Principled Estimation of Regression Discontinuity Designs. Jason, you want to go ahead and set up your presentation?
All right. Let's see here. All right. So should I just get going?
Yeah, go for it.
Thanks, Justin, and thanks for the invitation to this this great colloquium. I'm very excited to present here today. So I'm just going to kind of get right to it and jump into the paper. So this paper is entitled "Principal Estimation of Regression Discontinuity Designs," and I think you'll get a better sense of why it has that title in a few minutes. To give you a sense of how I kind of arrived at some of the conclusions that I did at this paper, you know, I actually went through the process of estimating a regression discontinuity design as part of my dissertation and thesis work, and it was quite a difficult process, I had to say. This is actually what I looked like as a grad student at Berkeley a couple of years ago. Very clean shaven, in relatively decent shape. And, just looked like a relatively young guy. During that time, I was working on this paper, which was eventually published in Electoral Studies, entitled Estimating the Gender Penalty in House of Representative Elections using a regression discontinuity design. And from writing this paper, I actually learned a lot about regression discontinuity designs, and I learned a lot about the publication process. And by the time that I published this paper, I had kind of like an Amish chic thing going on, where I had, I was just, working intensely and trying to figure out how I can best estimate these RDDs. And it was quite a difficult process. But the nice thing about going through difficult things in life is that you gain a lot of wisdom out of them. And the wisdom I gained from writing this paper was that regression discontinuity designs have a couple of problems that I think we need to fix. And this paper is really a means of attempting to do that. So what's one of the problems that they have? Well, the first thing that I encountered when trying to estimate this RDD was that I had so many choices as to how I can estimate a treatment effect. So, in a kind of general regression framework, right? So if you're doing an experiment and you estimate a regression model to get a treatment effect, you have, pretty much three types of choices you can make. That's on the left-hand side here. You have a dependent variable, you have a treatment, and you have some pre-treatment covariates if you choose to include those. With an RDD, you have all of those things, but you have many more choices. So you not only have the treatment, the covariates, and the dependent variable, then you also have to figure out what kind of, obviously the forcing variable is an important part, and that's more of a fixed quantity. But then you have to figure out, well, what kind of kernel do you want to use to estimate your model? What kind of bandwidth are you going to use to estimate your treatment effect? Which method are you going to use to estimate that bandwidth? Which data subset should you start off with? Which will affect your bandwidth and which will affect other things downstream? And what type of model will you use? Will you include interaction effects? Will you include square terms, Q terms, terms to the fourth, and so on and so forth? So the reason that this is a problem, all these degrees of freedom, is that it unfortunately creates negative incentives, let's say. It creates incentives to, kind of manipulate treatment effects in a way that helps the researcher. And this is just perfectly natural. And it makes perfect sense, right? If you could tweak some knobs and dials in order to better make an argument or increase the probability of publication, then I think most people, not most people per se, but many people will do that. And of course, in psychology research, we find this is called researcher degrees of freedom. And what we find typically is that the more researcher degrees of freedom that are available when conducting experiments and other types of studies, the more likely it is that there's a false positive result, right? Which is kind of expected. But RDDs have their own problems in addition to this, and that involves the number of observations typically used in the type of work that we do, where we do close election RDDs in political science. And so oftentimes we'll estimate treatment effects with a small number of observations, which also leads back to this problem of researcher degrees of freedom, right? Because what happens when you have a small number of observations? Well, when you include covariates, then your treatment effects will be pretty unstable. And you run into a situation where you can estimate very different types of treatment effects. You can get very different results depending upon whether you include a certain set of covariates or whether you exclude those covariates. You could also get a different treatment effect, in terms of whether you include a certain type of bandwidth or another, right? One bandwidth method or another, the bandwidth thing, and so on and so forth, right? So, pardon me. So let me give you an example of how unstable some of these treatment effects could be. Now, this is actually a study, and this is a kind of a preview of some of my results from the end of this paper, an empirical illustration of the application of the method I developed here. And now this is a study with actually quite a lot of observations. You could see that if you look at the columns which say original APSR, right? These are the original treatment effects from an APSR article published in 2018 by David Zacconi. It's actually a great article, and it's called Political Connections and Firm Profitability. I won't go into what it discusses, but it's a very good article which uses a regression discontinuity design. Now, Zacconi includes quite a few covariates in his original paper. And in the first column, you'll see that with the full set of covariates that he uses, he gets a, I'm going to highlight this here, 0.146 treatment effect with a standard error of 0.065. The bandwidth that was estimated was 0.113. And there were no covariates dropped here, right? That was just the full model with all the covariates originally included here. Now, when I apply my method, which effectively just trims covariates, as I'll explain in a minute, you can see that there's a huge difference in the treatment effect size, right? It changes to 0.102. The standard error remains roughly the same, and the bandwidth changes slightly. Now, this is only from dropping 4 covariates, right? So 4 covariates, a relatively large number of observations, and we get significant fluctuations in treatment effects. So you could imagine what the situation would be like if we had a smaller number of observations, right? We would get far more fluctuations in treatment effect sizes and standard errors in those cases. Now, you might think, well, okay, well, yeah, so the best thing really is just to get rid of covariates, right? But actually, as it turns out, that's not necessarily the best solution. And in general, it's not the best solution because there's a lot of great theoretical research by Kalanick, Catania, and Katiunik, and others who find that covariates increase the precision of treatment effect estimates quite a bit. So we can actually use covariates to improve our estimates, but we have to use them in a smart way, and that's what this paper is about. So how do we do that? Well, my argument in this paper is that the way forward is to look to the machine learning literature, which has done a lot of exploration on covariate adjustment of treatment effects in randomized experiments. Now, there's a kind of interesting literature emerging in machine learning, which combines causal inference and machine learning. And one of the better studies in that area, in my opinion, emerged around 2016. Blonares et al. and Vager et al. I believe that's the way his name is pronounced. And both of those authors published papers in which they basically just applied a lasso, which is a means of, and I'll talk about that in a second. It's basically an automated means of selecting out variables in linear models to randomized experiments where there were many covariates included. And they demonstrated that you can actually increase the efficiency of treatment effect estimates when you do this, and you could do so in a more principled way. And they actually argue that using this automated model selection procedure is a more principled way of estimating treatment effects. So the gist of this literature is that we can get the benefits of including covariates in cases where we're estimating linear models while minimizing the costs. And so this is really the kind of argument behind this paper, that we should continue to include covariates in regression discontinuity designs. We should even continue, from my perspective, to estimate RDDs where we don't have enough observations, or we don't have a large number of observations simply because there are certain limitations that we have, data limitations that we have in the type of work that we do. But one way to safeguard against these more pernicious effects of researcher degrees of freedom and unstable treatment effects is algorithmic selection of the covariates, which is exactly what this paper proposes. So now I'm going to talk a little bit about what the rest of this paper is about. And the paper is basically about an algorithm, a relatively simple algorithm that I had designed, which has a number of steps that allow for automated selection of covariates in regression discontinuity designs. So the 4 steps of this algorithm, which I'm going to go through in a minute, are researcher pre-treatment covariate selection. That's step one, and that's a decision that the researcher makes before estimating the model. Step two is applying what's called the adaptive lasso, and it's a certain flavor of lasso, which uses a different type of penalty term that I'll discuss. And there's a reason why I use the adaptive lasso instead of the ordinary lasso in this context. So that selects out the covariates that the researcher had included originally. And then finally, in step three, those covariates are selected out of the model. And in step four, the final treatment effect with the adjusted model is estimated using CCT or canonical-Catania and Titunic robust estimation methods for kind of double robustness. All right, so I'm going to talk about each stage of the estimation process and give you a brief applied example using the Zacconi study, and if I'm able to get to some simulation results demonstrating that this method actually does do a really good job of decreasing bias in treatment effect estimates in some circumstances, and also improving the efficiency of the treatment effect estimates in all circumstances, but particularly when there's a small number of observations. All right, so I think most of the audience here knows quite a bit about regression discontinuity designs. So I'm not gonna get into too many of the details about how to estimate an RDD, but the focus of this paper was really on local linear regression, estimation of local average treatment effects in RDDs, where you basically have a treatment effect, a dummy variable T, and then you have a forcing variable F, and there should actually be another F here, but that was missing. And so this is like one of the simplest models you can have, where you have this T dummy variable, you have the forcing variable F, and the dummy variable T, and then you have a forcing variable as part of the main effects, quote unquote main effects as well. And then added to that is, again, a very common practice that I argue is good, that is including covariates in your model to increase the precision of those treatment effects. So based on the basis of this model, let's talk a little bit about how the algorithm that I developed here alters the original model. So let's take a model such as this one, where we have the kind of the full local linear regression model. And the first step is, again, the selection of the x's in this x beta matrix. So that is really up to the researcher. I don't suggest any particular method of selecting covariates other than that they should be pre-treatment covariates, and they should be covariates that can potentially increase the precision of the treatment effect estimate. And there's also, of course, sample size considerations. If you're dealing with a sample size of 50, you probably shouldn't include 20 covariates and so on. So, but that's up to the researcher. So the researcher at this first stage, they select the covariates. And on the second stage, their model is subject to adaptive lasso regularization. So I'm going to explain what that is. The way that this lasso regularization works is a little bit different than ordinary regularization, in the sense that I actually tailored it such that it doesn't penalize any of the quote unquote main effects in the local linear regression. So all of these, the tau, gamma, and delta, right? None of these quote unquote main effects are penalized. The only thing that, the only variables that are penalized here are the actual covariates. So we start off with X, right? And then our goal in general, with the lasso method, is to choose some subset of those covariates, X, X, XS, such that we minimize the mean squared error of this model. Now, in previous papers, the ordinary lasso was used, and the ordinary lasso regularization looks something like this, where this is, you have your loss function, and you're trying to minimize you're trying to discover the parameter estimates through minimizing this function, which includes a penalty term, right? So the penalty term includes a lambda tuning parameter, and and for each covariate that's included, the absolute value of each covariate, of each parameter estimate, is included as a penalty for this model. And so this is called an L1 regularization penalty term, and it's L1 because there's a kind of absolute, because the absolute value of the parameter estimates are used to create the penalties. So the adaptive lasso is really a relatively minor tweak off of this model, but it's one that actually I think has important properties for social science research, and I'll explain that in a second. So the ordinary lasso, it does a really good job of selecting out covariates and minimizing mean squared error, but it's also subject to inconsistencies in the following sense. It might, and it certainly does in many instances, select different models, right? Each time it's run, depending upon how you tune your tuning parameter lambda, and how just other factors involved in the model that you're estimating, right? So this could actually be a problem in regression, with regression discontinuity designs, especially if we want to ensure that we have stable treatment effects, because what we might end up doing is we might apply the ordinary lasso, and the covariates it selects out are going to give you, you're going to end up with one treatment effect estimate. And then if you run the lasso again with a different cross validation, with different type of lambda cross validation, you might end up with a very different type of treatment effect. This is all kind of theoretical, but that could certainly happen. What the adaptive lasso has over the ordinary lasso is that it has what's called an oracle property, or the oracle properties. And this was actually proved by Zhao, who had published the paper talking about this adaptive lasso in 2006. And what Zhao basically argued is that while the ordinary lasso is not able to select a model from an ideal model, so imagine if you have a model that you want to estimate with covariates x1, x2, and x3, right? The adaptive lasso will consistently select the correct model, whereas the ordinary lasso will not select that correct model out. Right? Both of them are very good at minimizing mean squared error. It's just that the adaptive lasso is more concerned with selecting out covariates in a consistent manner, such that the quote unquote correct model is selected out. And so that's the reason why I chose the adaptive lasso for this context, because we want to have consistency, and we want to be able to say that this is that the model selected out by the adaptive lasso is the correct model. It also has some nice features which make it easy to incorporate kind of zero penalty weights for the RDD. All right, so what is the adaptive lasso? Basically, all you're doing here is you're estimating this loss function, but in this case, the penalty term has an omega j weight attached to the parameter estimate. And that omega weight is really simple. It's just 1 over the absolute value of the parameter estimate to the gamma power, okay? And Zhao in his paper says that the gamma power that performs best in his simulations is like 0.25 and 0.5, but that's something that that one can use cross validation for. Okay, so after you figure out what kind of covariates you like, then you pass this through the adaptive lasso model that selects out the final set of covariates to be used in the final estimation of the RDD treatment effect, and that set of covariates is X naught. Now, you might be wondering, like, well, how do you incorporate bandwidth selection here? Because there's, in political science literature, especially in Zacconi's paper, as we'll see in a second, there's a couple of different ways to incorporate to choose your bandwidth. Well, so I kind of go through the steps of under these two circumstances, like how this model would be applied. So when the optimal bandwidth is used, right, when we just let the IK algorithm pick our bandwidth, the adaptive lasso can be applied in one particular way, and then when the fixed bandwidth is used, the adaptive lasso can be applied in another way. And so when the bandwidth is fixed, the automated model selection occurs, like here's the main difference. When the bandwidth is fixed, the automated model selection occurs after bandwidth selection, whereas automated model selection, when the IK algorithm picks out the bandwidth, the IK algorithm is run first, and then the model is the automated model selection through the adaptive lasso is selected at that point, right? So that's really the main. That's how to deal with that situation of different types of bandwidths, right? So let me explain. And then finally, the final stage is just CCT robust estimation, as I'll show in a minute. And so in the interest of time, I'm just going to kind of breeze through this. So this is the applied example using Zacconi's paper, which is, again, a great paper on looking at the effect on profitability of having elected board members run for office in Russia. And Zacconi finds big effects. This is the actual model used to estimate the treatment effect in this paper. And as I had shown you in the beginning, when I apply the adaptive lasso algorithm, now notice that the algorithm really doesn't select out that many covariates. If you look at the original full set of covariates, it's these set of covariates. I'm not going to all of them, but you could find more information about that in the paper. But it's a lot more than 4. There are roughly 10 or 12 covariates, and the adaptive lasso method that I describe here selects out only 4, but changes the treatment effect significantly, and also does what we hope it would do, which is, of course, lowering the standard error and increasing the efficiency of the treatment effect. So this is the case where, in the first 2 chunks, this is the case where we have the optimal bandwidth selection situation, and then in the second 2 columns, so columns 1, 2, 3, and 4, this is a case where there's a fixed bandwidth of 5% chosen, and we get similar results. Again, big changes in treatment effect size, and nice reductions in standard errors. So these beneficial kind of properties of the adaptive lasso method are also demonstrated in the series of simulations. And in the interest of time, I'm just going to breeze through these simulations. They're a set of what quote unquote realistic simulations that I tried to create, where the treatment effect is 0.3. That's really the most important thing. And there's a set of covariates that are included in the original model. And the goal of the regularization here, the adaptive lasso regularization, is to select out the correct model. We see from this is where there were 2,000 simulated data sets created, and these are treatment effect estimates for each of those 2,000 simulations using the adaptive method and the conventional method. Conventional just being including covariates, including just covariate the original model with covariates. And so we see that we get, the adaptive lasso produces estimates that are a lot tighter, treatment effect estimates that are a lot tighter, around 0.3 mark, which is the treatment effect size. Okay, so and for this n equals 500 simulation, we see that with the variable bandwidth method, the adaptive method it decreases bias over conventional, and it does better in terms of percent coverage. We have about 95% coverage in the adaptive method, and 69% with the conventional method. And with fixed bandwidth, the bias kind of effects go away. The adaptive doesn't do that much better than conventional in terms of bias, but again, we're in a situation where it's much better. We get much better coverage and consistent coverage. Now, this is a series of simulations where there are 500 observations. But we'll see that the method actually does even better when we have fewer observations, which is part of the reason it was designed for. So we can see here that the adaptive method, the lasso method in red, stays pretty consistent, whether we have 100 or 400 observations. We get consistent coverage, which is exactly what we want, and we also get improved bias when the number of observations are smaller using the adaptive method in red. All right, so it looks like I'm out of time, but that's pretty much it. I hope I'm looking forward to your questions. Thank you.
All right, thanks for that presentation, Jason. At this point, our presenters are available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. We've already had a few questions come in, mostly pertaining to the first presentation, probably because people have more time to think about it. So I'll just start with those questions. Guy Moore asks, and this is about Patrick's presentation. Thank you for a very interesting presentation, Patrick, about concatenation of image features to BERT features. What are the benefits of using film over using zero or padded learned inputs for missing images and concatenating these to the BERT embeddings? Second, are you fine-tuning the entire model end-to-end, including BERT and ResNet weights?
Yeah, so I'm happy to answer that question. That's a really good question. Let's see, the first part is what are the benefits of using film over using zero or padded learned inputs? I think the main advantage of using film over just using a vector of zeros for missing images is that when we use the fully connected layer at the end for the classifier, that includes both a scalar term and a bias. And so the scalar terms won't be affected because 0 times the weight would just be 0, but the bias terms will be affected. So in backpropagation, the bias terms will be updated, even for observations that don't have an image. We could also, I think theoretically, we could use like learned inputs for the missing images, but that would take a lot of training and a lot of iterations. And one of the problems that we face is that we don't have a lot of tweets. So using a sort of, trying to avoid lots of training that is required would be really beneficial. And then was it trained from fine-tuned, the entire model was fine-tuned end-to-end? Yes, it was. So the BERT weights, the weights for ResNet 152, they were all updated in the fine-tuning process.
Pablo Barbera has a question for Patrick, and it's sort of similar to, it's not similar to, but related to one that I have. So Pablo's question is, how would your approach deal with combinations of text and images that contain contradictory information? So for example, I tweet out big crowds today, ironically, and then show an image with no crowd. And my version of this question is there information contained not in the picture itself, but in the fact that there was a picture? And what I mean by that is, like, you know, for example, with the police riots going on right now, the same video gets retweeted by a lot of people, right? The same image gets retweeted by a lot of people. And if you're retweeting that image, it's for a reason, right? And so basically that image signifies something about being mad at the cops or whatever.
Yeah, so so another really great question. So this is partially this idea of contradictory information was part of the reason why we wanted to include keywords about the image. Because if the image, say in this example, there's a tweet that says big crowds today, but in the image it shows no one, then the image classifier won't classify the image as queue or crowd or anything like that. It would just say things like whatever objects were in there. It could be a billiards table with no one around it or something, or random objects. So it can deal with contradictory information because if it was, say, not ironic, so big crowds today, and there was a line, then the classifier would learn the association between statements like big crowds today and keywords such as crowd, which then implies things like weight and things like that. But for observations where it does say big crowds today, but it doesn't include those kind of keywords, it will begin to learn that there are certain observations that present contradictory information, and you can begin to learn from that, if that makes sense. So that's really why the keywords are so important to this process, because the keywords allows us to have a deeper understanding of the contents of the image, which is then allows the classifier to know, like, okay, is this presenting image that's, or information that's coherent or not coherent? So that's really the role of the keywords here in that case. In terms of repeat images, so images that are shared a lot, this wasn't really a big issue in the data set that we dealt with, but that's a really good point. And I'm not too sure how the classifier would react to something that is shared repeatedly, what kind of associations it would learn with that. Because you're definitely right. You will learn, there's definitely something different about posts that include an image versus those that don't. And that's partially why, rather than just applying the film parameters directly to the BERT embeddings in a sequential manner, we use the transformer. Because the transformer can learn the relationships between the self-attention module at the beginning of that transformer film block, that can learn the relationships between the posts that don't have images and the posts that do have images. So that's really what that self-attention block is doing. And that's why it's so critical including that as well.
One reason I thought of that was not just because of Twitter, but also if you watch the coverage on Fox News and you watch the coverage on CNN, you get shown a completely non-overlapping set of images. Like, it's amazing that one network shows nothing that the other network is showing and vice versa. It's weird. A quick question for Patrick from Elliot Ash. How much of the gain do you get from adding the ResNet embeddings as predictors to the ensemble model?
Yeah, so we haven't added the ResNet embedding as predictors to the ensemble model. So this ensemble classifier is, I think, support vector machine, logistic regression, I think random forest, and a couple other things. And then it's a majority vote taken across all those classifiers. So that was the ensemble classifier. And we haven't added image features to that yet because the text BERT, using only the text and BERT, already outperforms that ensemble classifier in almost all categories. But that's actually a really good suggestion, because that could be another way of seeing how much effect the images have on classification performance in another context rather than BERT. So that's a really good suggestion. Thank you.
Question for Jason from Kaming Chan. I hope I pronounced that right. If I don't use any covariates because of insufficient observations, will lasso estimates still be possible and give a better estimation than conventional estimation?
Yeah, that's a really good question. And so, along with this paper, this paper is a package called adaptive RDD, and basically that allows you to determine which covariates you want to penalize. So there is a case in which the default here for the algorithm is that none of the treatment effect, the parameter estimate on the treatment effect and on the forcing variable and on the interaction between the two, none of those are penalized. However, if you have a model where you include, squared terms, cubed terms, and other types of iterations of interactions, you can penalize those. And if those observations are not, if those variables and the parameter estimates on those variables are not contributing to the model, then that actually, applying the lasso will actually improve your treatment effect estimate in terms of efficiency.
Well, we're almost right at 1 p.m. Eastern, so I'd like to thank our presenters this week, Patrick Wu and Jason Anastasopoulos, for being presenters. I want to mention that their presentations will be posted to our website shortly after this broadcast if you'd like to share them with a colleague or watch them again later. I'd also like to invite everyone to join us next week on Friday, June 12th, when we will host a talk entitled "Has President Trump Changed the Way Americans Talk About Immigration on Twitter?" by Bryce Dietrich of the University of Iowa, Nick Beauchamp of Northeastern, Jailu Yao of University of Iowa, and Yuhong Tai of University of Iowa. We will also host a talk entitled "A Latent Utility Approach to Missing Not at Random" by Nadia Liu of Princeton. Please see our website, www.methods-colloquium.com, to get more information about these talks. Thanks, presenters, for being here. Thanks, audience members, for being here. And I hope to see you next week.
Thanks, Justin. Thanks, Patrick.